Hi guys, in today's video we're going to talk about areas under curves. We're looking at this today because in many instances, especially in physics, the area under a curve can provide important information. Examples of this include the area under speed-time graphs, which gives us the distance travelled, and the area under force-distance graphs, which is the work done. What we'll do now is look at a few examples of speed-time graphs to look at how the area under the curve tells us about the distance travelled. In this example, we see the speed versus time graph for a particle moving at a constant velocity, v0, over a time capital T. Obviously, the distance travelled by the object is given by its velocity times the time of travel, which in this case is the area of the rectangle of height v0 and length t. In this next example, we've got a particle whose speed is changing over time. It starts stationary, but accelerates at a constant rate until it's at a final speed of Vf, over a period of time capital T. In physics, the displacement of anything that moves under constant acceleration can be given by s equals ut plus half at squared. We also have that the final velocity of a particle is equal to its initial velocity plus the acceleration times t. Since our particle starts with an initial velocity of 0 and moves over a time capital T, we have that the distance travelled equals half a t squared, and that the final velocity, Vf in our case, is equal to a times t. Combining these, we get that the distance travelled is equal to half times the final velocity multiplied by the time travelled. If we look at our graph, this is actually the area of a triangle of height Vf and base t. So the distance travelled is indeed equal to the area under that curve. In this next example, we have a particle that starts already moving with an initial velocity vi and accelerates until a final velocity of Vf after a period of time equal to capital T. Beginning again with the same two formulas, we get that in this case the distance travelled is equal to vi times t plus half a t squared, and that the final velocity is equal to the initial velocity plus a times t. We can rearrange this second one to get that the difference in velocities, Vf minus Vi, is equal to At, and then substituting this in, we get that the distance is equal to Vi times T plus half Vf minus Vi times T. Looking back at our graph, we see that the area under it is actually two separate areas. We have a rectangle of height Vi times t, and we have a triangle of area half Vf minus Vi multiplied by t, which is what we have in our equation there. So again, the area under the curve is the distance travelled by that particle. We could have also simplified this equation to be Vi plus Vf over 2 times t. This is actually the equation for a trapezium. We'll recall that a trapezium is a shape with two parallel sides of length a and b and height h, and whose area is given by the formula a plus b over 2 times h. Obviously though, in real life situations, the particle might move with a constantly changing velocity. And since we know that the area under the curve directly links to the distance travelled, we can use simple shapes to make approximations for that area. In this first case, we would approximate the area using a rectangle to work out an estimate for the distance travelled. In this next case, the particle is accelerating, but it's doing so at a non-constant rate. In this case, it would be most appropriate to estimate the area using a triangular shape. And in this final example, we see a case where the best approximation would be found by using a trapezoid or trapezium. In each of these cases, choosing the shape that best matches the overall shape of the graph gives the best approximation. In order to make use of these, we of course have to remember how to find areas of these different shapes. A rectangle should be fairly simple, area equals length by width. Triangle, area equals half base times height. And as we've already seen, the area of a trapezium is a plus b over 2 multiplied by the height h.